Okay, so I'm from Macquarie University up in Sydney. What I'll talk to you about today is the work we've done over the past number of years through various government funding organisations, the most recent one being SmartCrete CRC. And what I'll talk to you about is putting optics or optical fibre sensors, photonics, in sewers. So why would I do that? Next. Cool. Global wastewater utilities or water utilities in general have a big problem in that their ageing old concrete infrastructure pipes are corroding. These environments are very harsh, so you've got typically high humidity, over 95% in general, and you have this toxic H2S, hydrogen sulfide gas, being formed from the effluent itself. And then in this nice, unique, moist environment, you have bugs. It's a good environment for bugs to start growing, or bacteria on the roof and crowns and walls of these concrete sewer pipes. Now, it's these bugs that actually convert that H2S gas into sulfuric acid and start eating your concrete pipelines from the inside out. Now, the Australian water utilities spend over $100 million every year in management and rehab of such pipelines. So they want to know how fast their pipes are corroding. They want to know when the end of effective life is of their assets. But they want to do that remotely, long time data, and then can they predict when is it actually going to fail? So what does actual sulfuric corrosion attack of concrete look like? Here we have a bunch of concrete coupons just sitting in some sulfuric acid. This, of course, is a lot faster than what happens in a sewer. What you see there is an uptake of liquid into the coupon. Sulfur goes in, calcium leaches out. There's expansive byproducts formed, ettringite, gypsum, sediments, cracks, and eventually you have your failure of your asset. Now, the water utilities don't know when these are going to happen, so they could get a call and say something down the road here has burst. You need to come and see what's going on. So what we're trying to do is actually measure and analyse this rate of corrosion and the factors, environmental factors that cause it. So how do you do that? Well, you can't just go down to Bunnings and get a bunch of sensors and throw them in a harsh environment like this, because they're going to last about 3 days. You've got such high humidity, you've got the H2S toxic gas in there, which is an asphyxiant, so you just can't get those sensors. So you need long life sensors that can last a number of years. They have to be corrosion resistant, electrically passive, because a lot of the environments have a high methane content and can be explosive, and you want to get these sensors into these environments to access the data remotely. That is safer for the workers at these water utilities. So it turns out that optical fibre sensors, being a bit of glass, passive glass, fits this brief perfectly. And at Macquarie University, with our industry partners over a number of years, we've developed a complete photonic system of interrogation and sensing that actually works for these environments. Now, all of our optical fibre sensors are made at Macquarie University in the Optical node of ANFF. We've been there for 17 years now, Jane said. There's a paper here if you're interested on the capability of how we make the optical fibre sensors. They're based on Bragg gratings. I'm not going to go into any of that. Essentially, what I will say is that we are making very, very small modifications in the core of an optical fibre, which you can get commercially from the shelf. It's what all our telecommunications around the work evolved on. And by using femtosecond lasers, we can create these modifications in the core of the fibre to give us a nice unique reflection peak in spectral frequency. And by monitoring that frequency, we know that something has happened to this sensor itself. So, for instance, maybe the temperature's gone up, it's expanded, so these little periods here expand, and this shifts one way or the other, or strain is being pulled. So we then just monitor the light signals coming back to us from a deployed sensor and infer what's happened to that sensor at that location. I'm only going to talk about temperature and humidity. We have done other sensors as well, but I'll just keep it short as I can. Temperature is easy. You make a sensor in a fibre, you just let it hang in the air, it's going to expand and contract. Those peaks are going to move around, you can monitor that. Humidity is a little bit different. Humidity, you need to coat your sensor in a hygroscopic material, something that changes its volume with water vapour. So in this case, our optical fibre sensors are coated in polyimide. polyamide stretches when it takes on water, and then as the water vapour leaves it, it contracts and imparts that expansion and compression onto the sensor itself, which we can monitor as a shift in that frequency peak. We're using commercially off-the-shelf polyamide coated fibres, and OptoFab are writing the sensors through those coatings, so there's a reduced human touch there, I guess, and the reproducibility of these sensors as we make them, which is great. And then, of course, this guy here still reacts to temperature, so you need to have a little temperature sensor next to it so you can compensate. So one measures temperature and humidity, the other measures temperature on its own, and therefore you can get rid of that cross-sensitivity. Okay, so what have we done with these? Over the years, we've deployed them in a number of head spaces of concrete pipelines, pumping stations, treatment plants at Sydney Water and Melbourne Water. And this is a sample of data, a year's worth of data here, giving accurate humidity and temperature data over a full year. And this is the first long-term data Sydney Water have ever received in terms of humidity. And they then will use this data to infer models to see actually what's going to happen to their, I guess, surrounding pipelines in the future. So this was a great result. And 4 years later, these are still in the sewers, they're still in calibration, still working to spec, and they're actually picking up, I guess, events that are occurring within the environment they've been deployed in. So for instance, the humidity changes up and down, which are usually typically up at near 100%, are due to events that are happening in, say, a digester level, so they're increasing the wastewater sludge levels. We're picking that up in our humidity readings, so I guess there's some sort of fresh air intake associated with that event that's going on. So for instance, if they weren't monitoring their sludge levels, we could tell them things were actually changing and happening, and we can tell them remotely from my desk at work, which is great. So I've shown some temperature humidity sensors working, validated for at least 4 years at the moment. How do you measure corrosion? Well, you go back to that video and you remember they expanded, and so the concrete coupons expanded in that sulfuric acid liquid. Well, what we're hoping in a sulfuric acid gas environment is that coupons will also expand in time. So we've we've embedded a number of strain sensors inside some concrete coupons, hung them in the most aggressive environment Sydney Water has up at Manly at their treatment plant, and we're hoping that those optical fibre strain sensors inside those coupons expand in time. We can actually pick up a sequence of strain events to actually tell them how fast the corrosion is actually happening. So that's still ongoing. Everything I've shown so far has been relied on a commercial interrogation unit from a market leader, and with today's conversion rates, you're looking at least over 50,000 Australian dollars for one of those units to send out a couple of fibres with multiple fibre sensors on them. This doesn't sit well with water utilities. They say, great, you've got a sensor solution for us that works and it's passive and it's great. However, we don't want a sensor system that's going to cost $50,000 deployed at all our manholes or different locations remotely. We need something that is a lot cheaper than that. So there's nothing on the market, so we built one ourselves. And the way we did that was we assembled a bunch of commercially available components just from the telecoms industry. Optical fibres off the shelf, utilised OptoFab node at Macquarie, utilised the RPF from the New South Wales node at Sydney University for our references inside this box that we've built, our interrogation unit. We developed some new processing methods and we've tested it in the lab and outside in the field, and we are matching pretty much the same accuracy of that $50,000 box, but we're doing it for $3,500. So we are now working through with Macquarie University a provisional draft patent, and we are now, I don't know if it's stage 2 or gate 2, John can correct me, on funding from ANFF, where we're doing some market research with partner Tim, and that's currently ongoing right now as well. So yeah, really big thanks to OptoFab, RPF, ANFF for the work we're doing here right now. So I guess just to quickly wrap up, optical fibre sensors survive these harsh environments in wastewater sewer pipes, which is very meaningful for water utilities around the world. They can actually, in terms of their asset management, end of life predictions, And all this data that we're going to be generating for them over the years can then be fed into sort of these machine learning models, so we can actually then start predicting where utilities should spend their money and concentrate before events actually happen and cost them more. We've deployed at Macquarie now a scalable photonic system, which has your interrogation, your light sources, your detectors, and sensors that go with that. And I'd just like to point out that it's the sensor technology, optical fibre sensors that we've been developing through ANFF at OptoFab. It's application agnostic. It's not just for harsh environments in the sewer, it could be for other harsh environments, oil, gas welling, it could be for transport infrastructure, pavements, and structural health monitoring in bridges and your buildings, for instance. So optical fibre sensors and their technology can be utilised elsewhere, not just in this work that I've been doing for the last number of years with our industry partners. So I'll just thank once again OptoFab, RPF and AMC for the work over the last number of years, and I'll leave it there so I can get to lunch a bit quicker.
Thank you. Thank you, Mark. Any questions? John?
I just had a question. That little video you showed at the beginning with the concrete degrading and the hydrogen sulfide.
Yep.
Why were the different rates of degradation?
So I have different coupons with different formulations. The one on the far right that didn't go very fast was from a Sydney Water, a very hardened old Sydney Water core sample. The two in the middle didn't do much at all. They had like, I think silica fume in part of their, or silica fly ash or something in part of their, so yeah, they should be making pipes and that sort of stuff to keep it from corroding, but the pipes are hundreds of years old, they've already been in there, they can't change it, they can try to rehab with similar things like this. I actually want my coupons that I'm putting in the sewer to corrode super fast. I actually want to pick up events really quick and then make some sort of informed guess of how I'm relating to the wall in the environment that I've deployed my sensor in. So I actually want my coupon to go as fast as I can. So that video there was me with different mixtures trying to find the fastest mixture that can corrode. So when I throw it in a gas environment, hope the bugs grow on it, hope they convert this H2S gas into acid and corrode, I want it to go fast. I don't want to sit there and go, okay, there's a year gone, there's 2 years gone. I haven't picked up any sensor strain limit at the moment. We're about 6 months into that study, and I think I'm starting to see the first couple of sensors ping. So it's a lot quicker than what it would do if I hadn't changed my formulation or done certain things to the coupon surface before deploying. So watch that space.
Rowan?
Thank you, Martin. There's a very similar case study at some IP from the University of Queensland that monitored high voltage transformers, a company called Corrosion. It's just been sold to Schneider. They also are interested in monitoring temperature and the environment inside those high voltage transformers. I'm interested in the similarity between the two, in that you're both not directly measuring what you set out to measure, which is degradation of concrete, or in the case of transformers, water. Are you looking at adding chemical sensors in order to measure directly rather than indirect measurement?
So one, we could be measuring directly if the strain sensors show us something. Indirectly, yes, we're measuring temperature, humidity, H2S, they actually contribute to that environment. So if we know that we're corroding fast at some environment and there's some certain level of humidity or level of H2S, then you do some sort of venting to actually get rid of that. So yes, I agree, it's indirect and indirect, but they need to be measured as well in this case. Am I doing chemical sensors? That can all come down to how you transduce or coat an optical fibre to measure what you want to measure. So you could coat a fibre in, say, palladium and measure H2 gas concentrations, for instance. You could coat it in other polymers, say hydrogels, and maybe measure pH. So I have done some work in some of those things. They don't suit too well to high pH concrete or low pH acid. Some of those coatings can degrade, but in other environments where that's not an issue, it may be acceptable.
Please thank Martin first of all.